All right. So, any questions from the last time? Last time we just did some explicit examples, right? To show, I mean, to compute the Fourier series and Fourier transform, and to show the inverse problem. I mean, which was essentially, I mean, a lot of practice. And if you try to do that, you practice a lot your, this contour integral skills. Okay. I mean, that is something, that is one of the things you have to, after finishing this course, you should be experts on, this contour deformations and, Okay. So now we go to the last section of this chapter, and then from next week onwards, we will discuss the fourth chapter, which is differential equations. I don't know whether you already received it, the fourth lecture notes already. Okay, good. Yeah. Okay, so now we go to the discussion of generalized functions. Generalized functions, or sometimes it's also called distribution. Okay. I mean, some books would use the word distribution, some books use the word generalized function, but they mean the same. Okay. So the idea is the following. I mean, the motivation for this is essentially, I mean, it comes from physics. In fact, okay, one of the examples of this is Dirac delta function. Dirac delta function, which you have already seen, I think, in the quantum mechanics course probably, or maybe even before you have seen probably. Okay. Now, the theory of generalized function was developed later, I mean, after Dirac defined this delta function. So, in some sense, physics, from the physics point of view, this function was introduced, and then mathematicians later on developed into a mathematical theory, the theory of generalized function. So, the intuition for this delta physical intuition comes from the following thing. I mean, suppose for example, let's consider some Maxwell's equation, for example, say Gauss law, for example. So you'll have the equation will be divergence of the electric field. Okay, this is a Gauss law. That will be equal to the charge density, right? I mean, there could be some numbers, but basically it's charge density. So charge density, of course, I mean, you can imagine the situation that there is some object here which has some charge, which carries some charge, and there will be some charge density, right? The total charge is something, some particular charge, which is the integral of the charge density, right? The integral of the charge density will give you the total charge, Q. Q is total charge, let's say. So, for example, I mean, so this is kind of equation that you need to solve. So, given a charge distribution like that, then solving this equation, you find what is the electric field, which this charge produces, right? This charge will produce an electric field, and that you obtain by solving this equation, right? But in many cases, in physics, what you want to do is to simplify the situation, to idealize the situation, okay? The reason is that, I mean, why does one do that? The reason is that you don't want to deal with too many complications, right? When you first want to understand the fundamental idea, you try to make the simplest possible choice, not to clutter with the lot of other complications which are not central to the problem, right? So, for example, let's say you imagine this as a nucleus, for example. Suppose it's a nucleus, okay? Nucleus carries some positive charge, and then there will be electrons which go around it. That's the hydrogen atom, right? Now, nucleus, of course, has a size. I mean, it's not that nucleus is a point particle, right? It has a size of the order of something like 10 to the power of minus 15 centimeters, something like that. So it has a size, but I mean, as a first approximation, it is good to it's simpler to consider it as a point particle, right? It's in fact, I mean, if you think about the size of the atom, which is like 10 to the minus 8 centimeters, and this is, I think, 10 to the minus 13 centimeters, something like that. So the size of the nucleus is, I mean, to scale it, to see the scale of it, if you think of the size of nucleus as 1 centimeter, the size of the atom is 1 kilometer, I mean, the diameter. So from the point of view of this atom, nucleus is essentially a point particle. It's really, you can treat it as a point, right? And that's a good approximation, right? but in any case, I mean, so what do you do? So you want to think of it as a point particle, right? But at the same time, the total charge is something fixed, right? So that means, I mean, how can you accomplish that? So suppose you want to keep reducing the size, but keep the charge fixed. That would mean the density should become larger and larger, right? And in the limit where the point it becomes collapses to a point, the density exactly at that point is infinite, should become infinite. Everywhere else density is 0, right? But the integral nevertheless is some fixed number, right? So that is a I mean, so I can take the point particle limit by thinking of a dense, if I plot the rho, for example, okay, let me just plot in one dimension. I mean, here I should plot it in 3 space dimension, but this is impossible to plot it. So let me just take one of the directions in the space. Then it should be, I mean, as I reduce the size, so it will be something like this, okay. But the total integral must be 1 or q. Let me call it just 1. Let me take the example just 1. Say charge is just 1. The total integral must be 1, which means the area must be 1, right? So I'm thinking of a one-dimensional problem now, just one-dimensional problem. For 3 dimension, you just have to, I mean, draw it in 3 dimensions. So just take one-dimensional problem. Okay. So here I have, but then I reduce it, so it's going to become taller here, so that still the area is 1, right? And in the limit, you just get, I mean, this collapses to the point, but here the height becomes infinite, right? But in a very particular way, such that the area is 1 always. So this is the origin of the delta function. So in fact, what you say that rho of x is simply delta of x, okay, in this limit. Okay. So the property of delta function is it is 0 everywhere except at x equal to 0. So what is the basic property we want? Delta of x should be equal to 0 when x, for x not equal to 0. At x equal to 0, it is infinite. I mean, but the important point here is that the integral delta function, that's equal to 1. Okay. That's the important point. Or I mean, let's say anyway it is 0 everywhere, so you might as well just put from -1 to +1. It doesn't matter because outside it's 0 anyway. So any range, if you take any interval from -epsilon to +epsilon, okay, that integral will be equal to 1, because that the interval includes the point x equal to 0 also. Okay. So this is the idea. Now, of course, if you can, I mean, you can think of it as this kind of functions here, but it's perhaps better to think of, I mean, so you can take this function, I mean, a limiting. So you can take this, consider the delta function as a limiting function, right? You take a sequence of functions like this, okay? Then another function which is like that, and so on. You keep taking sequences of functions, and you might define the delta function as the limit of the sequence of functions. However, these functions are not very nice because these are discontinuous functions, right? So it is better to use some kind of sequences of functions which are themselves good functions, okay? Meaning they're continuous and so on and so forth, okay? So that is how this theory of generalized functions came, right? It was basically to define these delta functions in a more rigorous, mathematically rigorous way. Although Dirac had already introduced it many years before that. Okay, so let me, but before I discuss this, so in fact, so let's see how one can do this. So for example, if I just take a sequence of functions, let's say fn of x, which is, let's say e to the power of minus nx squared, okay. In fact, let me take that, get the normalization straight. Yeah. In fact, okay, in the notes, what is used is capital Dn. I just try to keep the notation of the notes. And the normalization is root n by pi. Okay. So consider the sequence of functions for n equal to 1, 2, etc. Now, all of these functions have this nice property that if you integrate dnx dx from minus infinity to plus infinity, it is a Gaussian integral, right? dnx is simply Gaussian. So substitute that. So you get here root n by pi e to the minus nx square dx. Now you can absorb this n inside the x by changing the variable called x equal to y divided by root n, right? So then this becomes simply e to the minus y square, and the change in the this variable becomes dy divided by root n. So root n cancels. Okay, so you get here 1 over root pi e to the minus y square dy from minus infinity to plus infinity, but this integral is simply root pi. So this is equal to 1. Okay. So for every I mean all of these dn's, they satisfy this equation. So the integral of any of the dn for any n is equal to 1. However, if you think about now, look at the shape. I mean, if you try to plot this dnx, if you try to plot this dnx here, dnx as a function of x, so notice that this Gaussian. So at x equal to 0, this is root n by pi. Okay, so at x equal to 0, let's say this is root n by pi here. Okay, and then it starts going down. Okay. I mean, I'm not drawing it very well, but you know, exponentially it will go down, right? And the width of this is obviously going to become smaller and smaller as n becomes larger, right? Because I mean, for example, let's say you take some particular point here. Let's say some particular point here for a given for that. I mean, so here the value is simply e to the power of. I mean, for this particular value, let's call it x naught. Is simply e to the minus n x naught square root n by pi, right? Now, I keep x naught fixed and start increasing n. I mean, suppose for a particular n, it has some value. There's some value. Now, I start increasing n. If I start increasing n, this is going to decrease. Even though there is the increase, I mean, this increases, but this dies off exponentially, right? So this goes much faster for large n, right? So this is going to become to come down, right? So that means this whole thing is going to become more and more sharply peaked as you increase n, right? In the strictly for n, I mean, so for any point x naught, if you take n goes in, so let's say I consider dn of x. So let me put it like this. So let's take dn of x at some point x which is not equal to 0. Okay, I want to evaluate dn of x at some point x which is not equal to 0. Well, this is nothing else but root n by pi e to the minus nx square. Okay, now you take the limit n goes to infinity. What happens to this? This becomes 0, right? For any non-zero x, that's the important point, right? Because if x is 0, then there is no exponential suppression. But when x is not equal to 0, this is not 0, and then there is as n goes to infinity, this just goes to 0, right? So indeed, this sequence of functions has the right property that we want for the delta function. For any non-zero x, the limit is 0, right? And for x equal to 0, of course, it blows up, because x equal to 0, this is not there, this is just 1, right? So you have root n by pi, as you increase n, it increases, but in such a way that the total area remains the same, right? Area meaning the integral of dnx is always equal to 1. This integral is always equal to 1, no matter what the value of n is. Okay, so this is a sequence whose limit you call I mean, this is a good representation of Dirac delta function. It becomes better and better approximation as you increase n. Yeah, so this is the starting point. So now let me define rigorously. I mean, sorry, yeah.
Physically, what this integral says, tell us physically. We got integral of d equal to 1. And how can we integrate this?
No, I mean, no, this you agree, right? This is true, right? This is true. So what this is saying is that this area, I mean, if I take the area here, I mean, this area, that is always 1 for any n. So you have, for a particular n, you have this area, and that integral shows that its area is 1, right? As you increase n, this becomes sharper and sharper peaked, but still the area remains the same. Okay? Always 1. Yeah? Physically, what it means, I mean, that's what we wanted, right? Remember, for the problem of the charge density, we wanted the charge density to be 1, right? The integral dx equal to 1, or 1 or q of something. So let's say 1. But we want to take the point particle limit. Okay, so the rho x should be 0 everywhere. I mean, for any x which is not equal to 0, but nevertheless, the integral of rho must be equal to 1. Right? So you can start taking. So you can take the rho n to be simply dnx. Rho x is equal to limit n goes to infinity dnx. Right? Because for every dn, when I do this integral, is 1. So in the limit as n goes to infinity, again the integral is 1. But at the same time, it has a property that this in this limit, this is 0 for any non-zero value of x, as we see here. Right? This goes to 0. So it has the right property. So this is the kind of taking the point particle limit, but at the same time to have a non-zero charge. Okay, so to define properly this kind of functions, these are kind of generalized functions, because obviously these are not normal functions.
What about if the function was discontinuous?
Sorry?
No, it was not continuous.
Which one?
The function g.
You mean this dnx? Yes.
Yes, if this function was not continuous.
Yeah, I mean, it's many things you cannot do, right? I mean, the point is that if you try to use this, I mean, it's not just, okay, this was just one little thing, I mean, one particular thing, right? But you would like also to be able to manipulate, say, taking derivatives of this rho, etc. No, you understand? I mean, a lot of manipulations you might need to do for a particular problem, right? I mean, this just tells you the integral is that, right? But now you can ask, for example, is there a meaning of the derivative of rho, right? Now, if you are going to use a sequence of functions which are themselves discontinuous, the derivatives will not make sense, right? Whereas if you are going to use dnx, this is perfectly differentiable any number of times actually, right? So you can define any number of derivatives of the Dirac delta function. I mean, we will see that now. We will see that. I mean, so that's why you want to use something which is completely smooth functions, so that all the operations you can carry out, like derivatives, particularly derivatives. Okay, so I need to properly define this. I need to introduce some concept, the concepts of. Let me see. Yeah. So there are some concepts. It's a definition. There are some functions which are called good functions. Okay. Good functions. Well, this is, I mean, as the name suggests, I mean, it has all the good properties, Okay. So what is a good function? So good function is, so a function which is differentiable any number of times, differentiable any number of times. And also has a property and goes to 0 at x goes to infinity. So a function, let's say a function of x so goes to 0 as x goes to infinity faster than any power, faster than any power of 1 over x. Okay, so like exponentially suppresses. That's what. So any power. I mean, faster than any power 1 over x to the n for any positive n, for any n. It goes to 0 faster than that. Okay. That's what is called a good function. Okay. So the example, I mean, in fact, this Gaussian is an example, right? This Gaussian e to the power of minus x square. This is an example of any number alpha times x square, right? This is an example of that because this is differentiable any number of times, right? And it goes faster as x goes to infinity. It's exponentially suppressed, so it goes faster than any power of x or 1 over x. So that's the example. In fact, you could also take any function. I mean, multiply by any polynomial, for example. If you multiply this by any polynomial, nth degree polynomial, to this Gaussian, that still has the same property. It's differentiable any number of times and goes faster than goes to 0 faster than any power of 1 over x as you take x to infinity. So these are all good functions. Then there is a definition of something called fairly good function. Okay. So fairly good functions have the first property, that is differentiable any number of times. Any number of time. And then for the second, you relax second property. Your second property, you say that, and as x goes to infinity, grows at most like a power law, like some x to some power n. It doesn't grow exponentially, that is. I mean, it grows only at most as some power of x for some n, for some finite n. So that's a fairly good function. It's examples of any polynomial, for example, is a fairly good function. Take any polynomial, any nth degree polynomial, it is infinitely differentiable, right? Any number of times is differentiable. In fact, after n derivatives, the next n plus 1 derivative, it vanishes, right? So anyway, and then all the other derivatives. So all the derivatives exist. And it grows at most as x to the n as x goes to infinity if you take nth degree polynomial. So that's an example of fairly good function. Okay. There are some nice things you can say about. We will come to that when we. I mean, one can show that, which will come later, that if you take a Fourier transform of a good function, if you take some, let's say, suppose some function f of x, which is good function, okay, then the Fourier transform capital Ft that you define from this is also a good function. Okay, so there are some very nice things that you can say about this good function, okay, which we will need, in fact. Yeah.
Okay, when you say that a polynomial is a fairly good function, so even if when you differentiate it you get 0.
Yeah.
Because if it is maybe a polynomial of degree 2, reaches a point where after differentiating you get 0. It is still, it doesn't matter whether you are getting 0, but
Is differentiable. 0 is just a particular function. It's just a constant function, right? Constant function is also differentiable. It just gives you 0. So derivative of 0 is again 0. So, but the point is it exists. You see, when you say something does not exist, it means either there is some discontinuity, right? I mean, so for example, let's say take an example. Let's say I take the function f equal to f of x equal to just modulus of x. Okay, this is, I mean, this is continuous function actually, but the derivative does not exist at x equal to 0, right? Or derivative is discontinuous, right? Because I mean the function is like this, no? If you draw it, it's like that. It's a modulus of x. So this is x f, right? So here if you take the derivative for the positive x is always plus 1, right? Whereas if you take the derivative here, it's minus 1. So df by dx is equal to plus 1 for x greater than 0 and minus 1 for x less than 0, right? So now this is discontinuous at x equal to 0. So then the second derivative will not exist at x equal to 0, right? So that kind of, so if you now take a second derivative d2f by dx2, it simply is not defined at x equal to 0, does not exist at x equal to 0. I mean, so that's, but if you have a constant function, derivative is 0, and then the next derivative is again 0, you know, so they all exist. It's just that it's trivial. It is 0, but okay. Yeah. Okay. So now how you define the generalized function? So generalized function is defined in the following way. So consider a sequence of good functions. Good functions. Again, let me use the same notation. I mean, you know, of course, sorry, just one thing, you know that the example that we gave about this Gaussian, that is differentiable infinite number of times. I mean, any number of times, right? In fact, from that, you can always write, say, the differentiation, say, take dn by dxn e to the minus x square. Well, you remember this was, this appeared in the Hermite polynomials, right? Actually, if you had multiplied by e to the x square, then that is what we defined as hn of x, right? Up to some normalization. So you can just this is the same as e to the minus x square. So you see that, and this is just nth degree polynomial, right? So these derivatives exist, and they are just given by Hermite polynomials times the Gaussian again, right? Yeah. So sorry, one more thing I should have added here. The function is differentiable in number of times, and if this function goes to 0 faster than that, and the function as well as its derivatives, as well as their derivatives, its derivatives, go to 0 faster than, right? Any power of, which is true for the Gaussian, you see, because dn e to the minus x square by dxn was a nth degree polynomial times e to the minus x square again. So also the derivatives go faster than any power, I mean, go to 0 exponentially actually. Huh? So this is indeed satisfied. Okay, so coming back here, so consider a sequence of good functions fn for n equal to 1, 2, etc., right, such that which satisfy the following property, which satisfies the following property, that if you take the integral of fn of x with any good function, so for all good functions gx, if this integral has a limit, n goes to infinity, has a limit, I mean the limit exists, limit exists, then this sequence is defines a generalized function. I mean, this is the definition of generalized function. Okay? And what I will do is we'll always use to distinguish between ordinary functions and generalized function, we'll use the Greek letters for the generalized function. So this sequence defines a generalized function. Let me call it phi of x. Phi. So I'm going to distinguish. When you see Greek letter, it means it's a generalized function. not an ordinary function, it's a generalized function. Okay. And so this defines to you, I mean, this defines to you, and you say, you say that so this limit, so this fn x g of x dx limit n goes to infinity, you define that as the integral phi x g of x dx. I mean, all these integrals are from, okay. So that's a definition. This is the way you're defining the generalized. So generalized functions are defined via integrals, you see, via their properties under integration. That is how you define the generalized function. Okay. So the important point is the limit should exist, you see. I mean, if you just take an arbitrary sequence, the limit may not exist, right? The important point is the limit should exist for any good function. Okay. Of course, for different choices of good function, there will be different limits. But when I say limit, I mean that this will be some number, right? For every n, this is going to be some number. So you get a sequence of those numbers. Those sequences that sequence should converge to a particular number. That particular number will of course be different for different g, right? In general. But here I am considering a sequence of in n, and that should converge to some value. And when it converges to some value, then that value is defined as the result of the integral of the generalized function with the g. So that's a definition of generalized function. Yeah.
So we have functions that goes faster than 1 over x raised to a, but its first derivative is not like a good function.
It's something which is faster than
1 over x raised to a, or any a, but its first derivative is not, that doesn't go like 1 over x raised to a. When we define functions, it's the function and its first derivative.
No, yeah, I mean, so if you say asymptotically, as x goes, some function s f of x, as x goes to infinity, let's say positive infinity, first, this goes like say 1 over x to the n. So then there will be subleading corrections, right? I mean, some subleading corrections in general. So I would say that df by dx will go like 1 over x to the n plus 1, right?
So why we need the condition?
Yeah, no, that's why I didn't add it in the beginning. Yeah, I mean, it's almost obvious that it will be true. Yeah. Okay. So that's the definition. Okay. Now it may happen. It may happen that you have some different sequence of functions. Let's say some f tilde n. Let's say, which also, so it may happen. They could. So consider another sequence fn tilde x. Okay, which again n equal to 1, 2, etc. And suppose that this also has a limit, f tilde n x gx integral dx. Sometimes I will not write the limits, but limits are always minus infinity or plus infinity. That this limit exists, and not only that, this limit n goes to infinity, it exists, and not only that, that happens to be also equal to the limit n goes to infinity of the first sequence. Okay. In that case, you say that both, this sequence as well as that sequence defines the same generalized function phi. Okay. Yeah.
Last result.
This one here.
Yes.
Yeah.
Can we say that the limit of the sequence is equal to the generalized function?
Yeah, the reason why one doesn't, say for all practical purposes, we physicists would think like that, right? We would just say that fn x in the limit. But as we saw in Dirac delta function at x equal to 0, it was not well defined, right? It was going to infinity. So it's in that sense, Dirac delta function is strictly not a function, because even though it's 0 at everywhere else, but at x equal to 0 is not defined. it's infinity, right? So that is why you never think of the generalized function. I mean, you are defining the generalized function only through its properties under integration, right? You never need to talk about generalized function as such. You always use generalized function under some integrals, you see.
Because if the integration doesn't depend to L, the limit can go in the integral and.
No, sir, I didn't understand. Repeat that again.
If the integration
Yeah.
doesn't depend on N, it's integral.
If the result of the integral does not depend on n.
Integral doesn't depend on N, the limit can go in here.
Sure, of course.
And
Yeah.
when we evaluate the limit of Fn, comparing with this result, can we say that this limit of Fn is equal to this function?
It's no. I mean, you see, because it's not a function. Yeah, I mean, you can think of it that the limit of n goes to infinity of Fn. You're asking the question, can I just call this as phi of x? Except that, I mean, this is not a function. I mean, you know, in any normal sense. I mean, like as we saw in the example of Dirac delta function, right? Those dn's that we defined before, the limit has no meaning actually. I mean, except for x not equal to 0, it had a well-defined meaning. At x not equal to 0, that was going to 0. But at x equal to 0, that limit didn't exist. No? Because at x equal to 0, these guys were root n by pi. It doesn't converge to anything as n goes to infinity, right? It just blows up. So in that sense, I mean, I think we physicists would think like this. I mean, we would just say, yeah, this limit is delta function, right? But mathematicians wouldn't like that very much. You know? That's the point here. Sorry, just 1 second. Yeah. Yeah. I mean, yeah, that of course, yeah. But I mean, so I mean, what I'm trying to say is that this you can, I don't know, let's put it in quote unquote. I mean, we can think like this, right? But it's not. One has to be careful because this is not well defined at x equal to 0, right? What delta function is well defined only inside the integral. You can say what is the property of delta function through its integrals with other functions, multiplying other functions to that. Yeah. So this is why, I mean, you see that if the two sequences give the same limit, the fn and f tilde n give the same limit for every good function g, right? Then of course, then obviously they will define the same generalized function, because generalized function is precisely that limit. So if the two limits are the same, I mean, this on the right hand side is just the limit n goes to infinity, right? So I mean, this, if you say that this gives you, defines for you some phi tilde of x, this generalized function, then we are saying that this integral is the same as phi of x gx integral, right? For every g. In that case, you say that the two phi and phi tilde are the same generalized function. Okay. So what I'm saying is that there can be many different sequences which define the same generalized function. As an example, if you take I mean, one can show, we will discuss later, that instead of dnx, if you just multiply this by any polynomial, pn of x, p some polynomial, let's say just 1 plus x, for example, times that. That is again it defines the same Dirac delta function. Okay. The only property of this function should be that its value at x equal to 0 is 1. Okay. That's all. And then this will also define the same delta function. The sequence, because after all, I mean, as n goes to infinity, I mean, this goes to 0 for non-zero x. So it doesn't care about what is the value of this function at x not equal to 0. It only cares about what is the value of this function at x equal to 0, and that should be equal to 1. Okay, so now let's see. So I mean, so okay, this is a definition. Now, what we can do with this? So, first of all, I would like to, well, I mean, I will just say the following, that when you use the word generalized, it means it's more general than the odd, yeah.
In general, our generalized function can be good function or not.
Generalized function is not a good function, but the sequence is a good function. The sequence which defines the generalized function is a good function. Yeah.
Otherwise, maybe the limit
Yeah, exactly. Yeah. It's a, yeah, the generalized function in general will not be a good function. So when we use the word generalized, I mean, when you say you are generalizing something, that means the original thing is also part of the more general framework, right? So, but originally what we had was just this notion of functions, right? Ordinary functions. So when you say generalized functions, we should also be able to, so those generalized functions must also include the ordinary functions, right? Somehow. But that's, you can show, for example, if you take any good function, you can always write it as a generalized function. Why? Because, I mean, say suppose there's some good function g of x. You can consider a sequence f n x, which is equal to simply g of x for every n. Obviously, it converges. I mean, right? Yeah, I mean, maybe I shouldn't use the same g here, something else, I don't know. Let's say some function h of x, which is a good function. Okay? Then I just I can just consider the sequence where f n x n equal to 1, 2, etc. This is just the h of x itself. After all, this is a good function, so you can use that, right? And then it's obvious that f n x with g of x dx integral has a limit, because for every fn, this is simply h of x. So obviously the limit is the same. So it's just equal to h of x g of x dx. So that limit exists. So I mean, in a trivial way, you can write every good function as a generalized function, right? I mean, meaning a good function can be written as a sequence which satisfies the property that the limit exists. You can also write a fairly good function sorry? No, converse is not true. No. So what is the converse of this? Let's see. No. I mean, so here is not a all I want to say is that, so I want to write this as a generalized function, right? So I have to find some sequence. Sequence.
Any function can be like as a sequence of function.
Yes.
And the converse.
Converse will be what? That any sequence of good functions will give you a define a good function. But that I already said that it's not true. I mean, Dirac delta function is not a good function. As a function, it's not a good function. I mean, it makes sense only as a generalized function. Delta function makes sense only as a generalized function, not as an ordinary function. Or, for example, even more, maybe you say that, okay, delta function still goes to 0 at infinity. So it's the only problem is at x equal to 0, right? But what about the step function? Step function is again a generalized function. Step function, I mean this you can write it as a generalized function, meaning that you can write down a sequence of functions which behave like this. Meaning at x not equal to 0, it's 0. X less than 0, it is 0. X greater than 0, it's plus 1. X equal to 0 is not defined, okay? But nevertheless, so this is, on the other hand, you see this doesn't die off at infinity. This remains constant, right? However, the sequence that you use, every element of that sequence is a good function, okay? But in the limit, it gives you this answer. Another example one can say, for example, 1 is a constant function, right? It is it's completely it's infinitely differentiable, but it doesn't go to 0 at infinity. right? But this can be again thought of as a generalized function. In the take a sequence like this, e to the minus x square over n square, for example. Okay, as n goes to infinity. I mean, so this is so this consider this function is f n x equal to that. Now, in the n goes to infinity limit, you see that's what is happening, because it doesn't matter, no matter what value you choose, what value of x you choose, right? For n goes to infinity, this goes to 0, so it's just 1, right? So this is, as n goes to infinity, is equal to 1 for any finite x. Right? So on the other hand, each function for a fixed n is for a fixed n, right? Each function is a good function because it's Gaussian, right? It's infinity differentiable and it goes to 0 faster than any power. So you have a sequence of good functions, but nevertheless, in the n goes to infinity, this defines to you a generalized function which is simply 1, in this case. So you can, and in fact, you can also do for any polynomial. Let's say some function is given, some polynomial is given of some finite degree, say mth degree, m degree polynomial. Again, you can write, for example, you can write fx times e to the minus x square over n square, px times this thing. This define this generalized sequence. I mean, say px is some polynomial, so it's of course infinity differentiable, right? But it doesn't die off at infinity. In fact, it could even go up, right? If it's mth degree polynomial, it goes like x to the m at infinity, right? But nevertheless, if you consider this generalized function, I mean this product p times that, that's a good function, because this is infinity differentiable, that's also infinity differentiable, so product is also infinity differentiable, right? And furthermore, there is a Gaussian here, so no matter what this m is, this is always going to die off very rapidly at infinity for any fixed n, right? But now you see, if as n goes to infinity, this becomes irrelevant, right? This becomes just 1. So that will define to you this. So p of any polynomial can be represented as a generalized function again. So in this sense, generalized function is a generalization, really generalization, right? Actually, here I needed something which was so this is an example of a fairly good function, right? So take any fairly good function. Fairly good function is this something which is infinitely differentiable and goes to I mean, at x equal to infinity, x goes to infinity, it goes at most like a power law, grows at most like a power law. So polynomial was an example of that. But any fairly good function I could have taken, and it would give you this. In fact, you can also even do more than that. I mean, you can. I will not go into this, but you can even do a bit more than this, and that's worked out in equation in page 229. Page 229, where basically, I mean, you can even take some functions f of x which need not be infinitely differentiable, but you can still write down a corresponding sequence, which converges to that. So there are some, but I will not discuss that. I mean, all I'm trying to say is that, I mean, you can more or less all the ordinary functions you can represent as a generalized function, but generalized function can contain more than just ordinary function. So in this sense, the word generalized it can be justified, this word generalized. All right, so now let us see what other manipulations we can do. Yeah. See. Yeah, there is another thing I need to say, another definition. So there's also a definition of regular points. So there is say I'm given again a generalized function. So let's say I have the sequence f n x for n f n x, which defines a generalized function. A generalized function phi of x. I mean, what that statement means is that the limit exists of the integrals of this f n x. The limit exists. That's what it means. So this statement just means that. So it will define a phi x. But I mean, so in general, see, phi of x cannot be thought of as a function, right? As we already agreed, like Dirac delta function, you cannot think of as a function, because at x equal to 0, it's not well defined. However, at x not equal to 0, there's no problem. Delta function is in fact 0, right? I mean, so it may have. So what is the meaning of that? So the statement is that, I mean, if let's suppose limit. Remember, the way it is defined here is that if you take the integral f n x g of x dx, this limit exists. That is a statement, right? That is a statement for this, right? But now suppose that there is some x for some, let's say for some x naught, it happens that limit of f n x itself exists. Limit n, sorry, n going to infinity exists, and so say this limit n goes to some function, I don't know, some function f of x, okay, where x is in some neighborhood of x naught. Okay, so there is, so take x naught, say there's some point x naught, and consider a small neighborhood around x naught. So, and if this happens to be true, that f n x converges to some function f of x in that neighborhood uniformly, okay, then x naught is called a regular point. Then x naught is called a regular point. Okay. And f of x to which it converges is called the local value of the generalized function. Right? And f of x naught is called the local value of the generalized function phi of x. So in this sense, so example was, if you take example, this dnx, which we defined earlier, which defined the delta function, the Dirac delta function. So for this, any point x naught which is not equal to 0 is a regular point. Okay. Because you can always find, I mean, given any x naught, so here is my 0, x equal to 0 here, and choose any point x naught, okay, then you can always find some neighborhood which does not contain 0, okay, and in that neighborhood you can find you can show that this converges uniformly to x equal to a 0 value. Okay, so the dnx will converge uniformly in this neighborhood to 0. Okay, so x naught is a regular point, and the local value of the delta function at x naught is 0. So there is some. So at the regular points, you can really think of the delta function, I mean, the generalized function as an ordinary function there. But then there are this point here where you cannot think of it as an ordinary function. Okay. So this is the idea here. Okay. So now, what other manipulations we can? So what are the kinds of things we can do? Well, for ordinary functions, we can do many things. We can add two functions. You can multiply any number to a function. Actually, the set of functions form a vector space, right? So can we do similar things with a generalized function? That's a, obvious question. You can, so the question is how much we can move, how much things that we can do with ordinary functions we can also do with generalized functions. So that's the next question that you can ask. So for example, adding functions. So for ordinary functions, we know if I'm given f of x and g of x, then I know what is the meaning of adding this function. In fact, any number times a function f plus any number times function g, I know what it means to add. So can I do, so now suppose I'm given two, let's say phi and something else. Now I'm running out of, let me use alpha. Alpha, a Greek letter. The Greek letters are always generalized functions. No? So I'm given two generalized functions, alpha and beta. Oh, sorry, this alpha, no, I should say a and b. A and b are numbers. So if I've given alpha and beta, is there a meaning of a alpha plus b beta? Is there in any way I can define that? So this is a generalized function, that's a generalized function. Can I say that there is, can I give a definition to such combination? Can I meaning to such thing, which is again a generalized function? Okay. Well, again, it's very straightforward, because if it's a generalized function, I can write this as some sequence of functions, right? I can represent this generalized function in terms of some sequence of good functions, right? Similarly, this will be represented by some sequence of good functions, say b and x, right? Then consider a sequence now. So now consider a sequence of good functions, alpha, a n x plus b n x. Sorry, this, I hope you won't confuse the symbols. I'm using the same a, I don't know. This is a number. This a and b are number, but this a n x and b n x are good functions. Okay. So a times this number times a, this functions, plus this number times this functions. This will again be good function, obviously. Sum of two good functions is again a good function, right? So now take the sequence, and so you can ask the question whether this sequence converges in the sense that, which is needed for the generalized function. So let's check that. So we want to check whether this limit exists. A n x plus b n x multiplied to any good function g of x. This is gx is any good function, and we are asking the question whether this limit exists. Okay. But that's obvious, because this is the same as a times the integral dx a n x g of x plus b times the integral b n x g of x dx, and the limit for each of them exists, right? Because by definition, this sequence is defining a generalized function alpha, this is defining a generalized function beta. So the limits, each of these limit exists, right? And in fact, this limit is what we call dx, what we define, what we denote by this notation, right? This limit exists, and this limit is simply beta x g of x dx. So you see that, so this simply gives you a times this number, a times alpha x plus b times beta x integral of times g of x dx. So you see that, the usual operations that you do for ordinary functions, it works here. The main point here to show was that this sequence also converges, right? Given the fact that this sequence converges in the sense of the integral, this also converges in the sense of integral, right? Then this sequence will also converge. That is the main point to prove here. Okay. Now, what about, okay, that was fine, that was just a vector space structure. But now, for ordinary functions, we can also multiply two functions, right? And that gives you again a function. Multiplication is again defined by pointwise multiplication, right? Now, can we do something like that with the for the generalized function? So, can I erase this now? This part? Yeah. That I can erase. Yeah. You can also, so we can now multiply. So this is the second point. We can multiply. I mean, we can multiply. We can give a definition of multiplication to some generalized function. Multiply this with some generalized function with a fairly good function. You can define this such a concept. Again, it's essentially the same because let's see. So let's say I'm given a fairly good function f of x, and I want to define what do I mean by this. So I want to give a definition. What is the meaning of this? So we want to give a meaning to this. To this concept of multiplying a fairly good function to a generalized function. Okay. So once again, let's suppose that fn of x is a sequence which defines the generalized function phi of x. Okay. I mean, the fact that I'm talking about a generalized function, it means that there is a sequence which defines. So take this sequence to be fn of x. These are all good functions. Now, just multiply, just now consider another sequence. Take a sequence of f times fnx, fx times fnx. This is also a sequence, right? N equal to 1, 2, 3, each of them, this product, these are ordinary functions, right? I know what I mean by multiplication, just pointwise multiplication. Furthermore, you already know that a product of a good function with a fairly good function is again a good function, right? Remember the discussion? I mean, both fairly good function and good functions are differentiable any number of times. So product is also differentiable any number of times. Now, what was important about the good function is that it is exponentially, I mean, it's suppressed faster than any power, right? Now, f of x is a fairly good function. It can at most grow as some power law, right? So product will again be exponential, I mean, suppressed faster than any power. So therefore, it's again a good function. That was the idea. So this is again a good function. For each n, this is a good function. So consider now the sequence of these functions. So the question now is that does this sequence converge? I mean, does this sequence define a generalized function? Okay. So that's the question. So we are asking the question that if I take any good function for all good functions g of x, if I take the element of the sequence which is fx times fnx and multiply this to g of x and integrate, does the limit exist? Does it exist? That's the question. But we already know, I mean, the fn's defined generalized function phi of x. What it means that the integral of fn with any good function has a limit, right? But you see that this thing is the same as fnx times f of x g of x integral dx, right? But this guy is a good function again, right? This f is a fairly good function, g is any good function, so product is again a good function. So by definition that this defines a generalized function, we are saying that this limit exists, right? So therefore, so this limit exists. We are saying this exists. and therefore this limit exists, right, because this is the same as that actually. So we are saying that this also gives you, defines a sequence, I mean this sequence again defines a generalized function, right, and that generalized function is simply denoted by this symbol f of x times phi of x. What else can one do? But one must be careful. The product of two generalized functions is not defined. I mean, there is no meaning to that. So here we have a product of a generalized function with a fairly good function. That is defined, but product of a two generalized functions is not defined at all. Okay. There is no meaning. I mean, there is no meaning to that. I mean, okay. Okay, so yeah, now the next concept. I mean, basically the problem is that I mean, if you try to do something like this, suppose I am given two generalized functions alpha x and beta x, right? This corresponds to some sequence, let's say a n x. This corresponds to some sequence b n x. Okay, so the integrals of each of them multiplied to some good function exists. But now if you try to do the similar thing, I mean, what were we doing? We're just taking the representative good sequence and multiplying by the whatever we are given, right? Now if you try to do something like this, so you might consider something like this, a n x times b n x, and ask the question whether this sequence is defines to you some generalized function, right? You might try something like that, but you cannot show anything, because you see that what this means is that you have to show that a n x, b n x, g of x, this integral, the limit exists. This is not guaranteed by the fact that the individual a n and b n have the limit, but this product may not have a limit. So I mean, you cannot say anything about this product of generalized functions. Okay, that's not simply defined. Okay, so now let's come to the important thing, differentiation. What do I mean by taking derivative? I mean, can I define a notion of derivative acting on a generalized function? And that will be a bit surprising, that in fact you can define. That's quite a bit surprising, that we'll always be able to define a notion of derivative of a generalized function. Okay, so let's talk about the derivatives. Derivative. And so derivative of some generalized function, let's say phi. So how will you define? Well, so suppose phi of x corresponds to sequence f n x. This sequence defines to you this generalized function phi of x. Then obvious thing you will try, I mean, is just to take the derivative of these guys and consider the sequence of those. Okay, so let us consider. So let me so I say this sequence defines generalized function phi of x. Okay, then consider the sequence dfn x by dx. Okay, this again is a good function, because as we saw, any derivatives of the good function is again a good function. Okay, so this is also a good function. Okay, so now consider the sequence of these functions. Now again you ask the question whether this converges to a generalized function. Okay, so let's do that. Let's try that. Let's check this integral dfn x by dx g of x for any g, any good function g, and we are asking the question whether this integral has a limit as n goes to infinity. Okay. Now here, of course, I can do a partial integration. Right? This is ordinary. This is a good function. That's a good function. Product is also a good function. You can just do an integration by parts. Okay. So the one term will be, the boundary term will be product of fn times g, but that will vanish because the good function vanishes at infinity, right? So you don't have to worry about the boundary term. So this is nothing else but minus infinity to plus infinity fn x dg by dx dx integral, right? And that limit exists, right? Because fn by definition was defining the generalized function, and dg by dx is again a good function. So this limit exists, and this is what we were calling this limit as n goes to infinity exists, and we called it phi of x dg by dx with a minus sign. The minus sign is this minus sign here. Okay. So we have proven that this sequence again defines a generalized function, and we will call whatever the generalized function, we will just define that generalized function to be the derivative of this phi of x. So this limit exists, and therefore this defines some generalized function which we will call as a definition of the derivative of phi. So see, we are defining. You see, now it's a new object, right? So it's a new object. Generalized function is a new object. You have to give your definitions, right? You have to give a definition. What do you mean by derivative? What do you mean by? But they should all make some sense. You see, that's the whole point. It should make some sense. So now we are. So what we have proven here, that this sequence defines a generalized function, and we will call that generalized function as the derivative of the original generalized function. And that definition makes perfect sense, because you see, so this limit, then we are saying that this is the same as integral d phi by dx g of x dx. Now look at this, the first term here, I mean this limit, sorry, I should say the limit. You understand what I mean? This is a limit n goes to infinity. This is equal to that. So now look at the two sides. This is equal to that. But that makes perfect sense, right? Because if you just try to do the integration by parts, like thinking of it like normal, what you do. I mean, like normal for normal functions, you do integration by parts, right? I mean, so in other words, if you put that together, two sides, then what we are saying is that d phi by dx g of x plus phi of x dg by dx, that integral is 0, right? This is of course, I mean this, so what I'm trying to say, this definition is it makes sense, you see. So this is the notion of a derivative. Okay, so that's one thing. So from this point of view, you see, the derivative always exists. I mean, if you define this way, if you give this as a definition of the derivative, then this always exists for the generalized function. Right? That's a bit surprising though, because as we saw, I mean, in fact, we will see also that the step function, this step function can be thought of as a generalized function. Okay? But if you think of it as an ordinary function, the derivative does not exist. At x equal to 0, the derivative does not exist. But if you view it as a generalized function, that you can define a notion of derivative. Okay. Okay. So now what is the next point here? Yeah, now the Fourier transform. Is there something else? I mean, you can prove similarly, but just lots of things. I mean, you can prove. You can, I mean, prove several things. I mean, just by the same steps. I mean, it's all written in 232, page 232. If you look at page 232, section. I mean, the whatever under the heading linear change of argument. I mean, meaning that you know, if alpha x is a generalized function, then then you can also define something like if you make a change of variable ax plus b, okay, you can again define a generalized function. So that's like when you change a linear change of variable, you can define a generalized function. It's simply by, I mean, as you would imagine, this has some sequence of functions, and consider now another sequence of functions which is simply ax plus b with the argument that this will define to you that. So there are several things you can prove. For example, the product f of x alpha x, where fx is a fairly good function. Again, you can take the derivative, use this definition of derivative, then you can show that that's the same as df by dx alpha x plus f d alpha by dx. Okay, you can please try to check this. I mean, as I said, this notion of derivative that we have given makes sense. I mean, it's meaningful. So this also is one of the meaningful things that you can do with the derivative. You can check whether this is satisfied with this definition. Is it satisfied or not? So check that. Okay. Now let's go to the other Fourier. Oh, so time is going. So Fourier transforms. We can define Fourier transforms of these things. Okay, but before proving the writing on the Fourier transforms, let us consider the following thing. So suppose g of x is a good function. Okay. Then consider the Fourier transforms of it. So g of t, which is 1 over root 2 pi dx g of x times e to the minus I dx, right? That's a Fourier transform. Okay, so first statement you would, it turns out that this function is also a good function. Okay, this is quite, I mean, so yeah. So how do you see this? So for it to be a good function, we need to prove two things. One, it's infinitely differentiable. Any number of times is differentiable, and it goes to 0 faster than any power of 1 over t. So let's take derivatives. So let's say I take n derivative or m derivative of g. Okay. Well, that is, just take the derivative here. So you find this is 1 over root 2 pi minus infinity to plus infinity, and you get here, every time you take a derivative, you get it, yeah. Sorry, minus ix, yeah. So you get here minus ix to the power of m g of x e to the minus itx dx. Okay. So that's fine, and this integral is perfectly well defined. Why? Because you see, I mean, the only possible problem could have happened as x goes to infinity. Because I mean, now that you are increasing the powers here of x, this will blow up as x goes to infinity, right? However, this is a good function. The good function is suppressed, right? Faster than any power of. So this integral exists always, right? So this exists. Yeah. See, this is where I mean, we are really using the fact that the g of x goes to 0 faster than any power of x. 1 over x. But now we want to prove that this g of t, in fact, not just g of t or any derivative, also goes fast to 0 faster than any power law. So we want to prove that. So to do this, let's now just try to use this trick. You can write. Yeah, there's an integral here. I can write it as d by dx times, I mean, this object I can write it as e to the minus itx divided by minus it, right? Because when I take, I mean, this exponential, I can write it like that. And then you can do an integration by parts. The boundary term disappears because the g goes to 0, right? So there is no boundary term. And then you will just get derivative acting on this combination. I mean, this is a polynomial, right? So this times g is again a good function. This product is again a good function, Okay. So you just apply these derivatives there, and in fact you can keep doing n times, right? So you can write this guy as n, and then you just take n power of that, because every time a derivative hits here, you get a minus IT factor which will be killed by that, and you can just do n partial integrations by part. Okay. So this is the same as 1 over root 2 pi, and then this is, you can take it out of the integral. So you get here minus IT to the power of n, and then you have this integral plus infinity dn over dxn. Okay, there is a minus 1 to the n, okay, because every time you do integration by part, there's a minus sign, acting on minus ix to the m g times g times e to the minus itx dx. Okay. So this quantity is equal to that, but this is, so if I just take the modulus of this quantity, so if I take modulus dm gt over dtm modulus, well, that's going to be the modulus of that, right? So you find this is equal to, okay, 1 over root 2 pi 1 over t to the n, t modulus to the n, and the modulus of this integral dx dn by dxn. Okay, since I am taking modulus, I can forget about minus I, etc. So you get here x to the m g of x to the minus itx, modulus of this whole thing. But then you use the fact that the modulus of an integral is less than or equal to the integral of the modulus. So this is less than or equal to 1 over root 2 pi times 1 over t to the n times just the integral of this dx modulus of this. Okay. And that is fine, because this product we said is a good function, and derivative is again a good function, right? And that integral will exist because it's sufficiently, it goes to 0. So this integral exists as some number, okay? But so what it is saying is that this guy, this modulus is less than or equal to some number divided by t to the n. For any n was arbitrary, you see. So it's telling me that this guy goes to 0 as t goes to infinity faster than any power of t, because n was arbitrary. You could choose n as large as you wish, right? So it's a, so this is so this derivative. So with this implies that dmg over dtm goes to 0 as t modulus of t goes to infinity faster than any power of t. Because n was arbitrary, you could keep increasing n, million, billion, trillion, you know, you can, but for everything it's some. Okay, so that is one thing. There is one statement. The second statement we need to prove I was hoping to finish this today. Is there any question here? I mean, is it clear? So the statement is that this guy is again a good function. Okay. But now we can also say one more thing. Now we can take again the inverse Fourier transform, right? And it will turn out that the inverse Fourier transform exactly gives you back g of x. You see. So the Fourier transforms work very nicely for these good functions. So now you take the inverse Fourier transform, g of t e to the itx dt and this will turn out, we will prove that that's the same as g of x, the original good function, right? Actually, probably it already follows from the theorem, right? I mean, the Fourier transform, the theorem was the first theorem, which was, I think, that if the modulus of this function that you are taking the Fourier transform of is what do you call, is integrable, okay? Then, so I think it was the statement was this, that if modulus of this function is integrable, okay, then the inverse Fourier transform gives you, so the inverse Fourier transform. So first you define that, then this guy will be equal to half of g x plus 0 plus g x minus 0. Okay, but that's okay because g is continuous anyway. So then it will give you a g of x. Yeah? But remember, we didn't prove this theorem. We just stated the theorem, right? But in this case, you can explicitly prove it. That's the point. Huh? So let me just go through the proof, because here it was, I just stated the theorem. We didn't go through the proof of that theorem, right? But here you can actually go ahead and prove it all the way, and it's not very difficult to prove this, because the function is a very good function. I mean, it's a differentiable, continuous, and dies off sufficiently fast at infinity, so you can actually prove it. Okay, so let's try to do this here. So let's compute this integral. So g of t is defined here. So let's so this is the same. So this is the same as 1 over 2 pi. I mean root 2 pi together, and I have dx. Now let me not use the same x, because this x is here. This is a dummy, right? So let me use y, dy, g of y, e to the minus I t y. That is the g of t. That is a capital G of t. So that I substituted there. Then I have to multiply this to e to the I t x, and then integrate dt. Okay. So this integral is a y integral, and then there is a t integral. Right? I just substituted gt. Actually, so let me do the following. Instead of considering this, let's so here this is what I have to prove, right? But instead of directly proving this, let me try to prove the following statement. I mean, let's define something else. Define something like this. Let me call it y minus 1/2 epsilon y square. Okay, integral. Sorry, epsilon t square dt. Consider this object. Okay, and let me just call this as some g tilde of y. X, let's put here x. G tilde of x. Okay, this is not the same as what we want to prove. In fact, let me also put here epsilon. Okay, because it depends on obviously epsilon. Okay. But in the limit epsilon goes to 0, which is what that integral is, right? We want to prove that in the limit epsilon goes to 0, g tilde x is the same as g of x, right? That's what we want to prove. I mean, the reason why I have put here epsilon, because this will give you a Gaussian suppression, right? Although this already gives you a Gaussian suppression, I mean some exponential suppression, but I just keep it as for convenience. Okay, now substitute this g of t inside here. So that's the same as you have a, so let me write it like this. You have minus infinity to plus infinity, and then g of t times, okay, gy, dy, dy, minus infinity to plus infinity, and then there is an exponential e to the minus ity. Okay. So, I mean, all I've done is I've replaced the capital GT. Capital GT was all of this, right? there's an there's an extra 1 over root 2 pi also, which makes it 1 over 2 pi. Maybe I did too much in the one line. Let me just, I'm getting a bit worried because we're running out of time. Okay, so this is same as 1 over root 2 pi, and then use this definition of this thing with a dummy. I mean, this x, I don't want to use same x here, so I put here y. So there is another 1 over root 2 pi dy gy e to the minus ity, and then you have plus itx minus half epsilon t square dt. Okay, that's the, there are two integrals here, y and t. Okay, now the point here is that this object, I mean, this thing is just a Gaussian, right? I mean, this you know how to integrate. This as I integrate the t. First, do the t integral. Okay, so there is a dt integral and the dy integral. First, do the t integral. Okay, so what is this exponential? This is simply the integral e to the minus 1/2 epsilon t square plus I t x minus y, right? dt. And this you remember from the second chapter, right? So the result of this integral was, you make it into a whole square basically. So it was, do you remember anything, I mean, about this result? I mean, you have to make it a whole square. So what is it, minus half, okay, epsilon, I take it out. So you get here t square minus I t x minus y minus 2I t x minus y over epsilon, right? And then you can write it as a whole square, which is minus half epsilon t minus x minus y over epsilon I times that whole square, correct? I'm just making it into a whole square. So if you, this gives you a t square, and then the cross term gives you that factor, but then I have to subtract the square of this, and the square of that gives you x minus x minus, because I square minus x minus y square, and there's a minus here, so I have to subtract actually, right? So this will give you minus x minus y square divided by 2 epsilon. Okay, so that I just use the trick. So the result of all that I can just write down now. So g tilde of x simply becomes 1 over 2 pi, yeah, 1 over 2 pi from here. Then I still have the dy gy integral, and then I have e to the power of minus x minus y square over 2 epsilon, and then I have the integral of that, and that gives me, do any of you remember what it is? There is a 1 over root epsilon, because I have to scale that, root 2 over epsilon, right? There is a root 2 over epsilon and pi, root pi, right? So root pi, 2 pi over epsilon integral, correct? I mean, if you remember correct, I mean, this is a Gaussian integral, gives you that. Okay, so this is what I have to do now. I mean, this is what is g tilde. Now, on the other hand, let's, I can also write g of x. I mean, so I can write g of x as the following: 1 over 2 pi, maybe root 2 pi epsilon, integral dy g of x e to the minus x minus y square divided by 2 epsilon, right? Is that correct? Is it correct? Yeah, I mean, it's again the same thing, right? Because you can scale it. I mean, g of x, this is, I'm integrating y. So this g of x, you can take it out. That's not a problem, right? And that's just a Gaussian. And does it give root 2 pi or epsilon? I'm not sure if. No, so yeah, this integral gives you what? Does it give you root 2 pi epsilon? Because I can scale root 2 epsilon, so root 2 epsilon up, and then the integral is root pi, correct? So that this integral gives you root 2 pi epsilon, that's why I divided by root 2 pi epsilon to give you 1. Okay. So I just taken g of x equal to g of x times 1, where I have written this 1 as this Gaussian integral. There is a reason for that, because after all what I want to prove is that this minus that in the limit epsilon goes to 0 goes to 0. That is what I want to prove, right? I want to prove that g tilde x in the limit epsilon goes to 0 is equal to g of x, right? Okay. So this is what we have, and now I can take the difference between the two. So let's take g tilde x minus g of x. Okay, that is, you see, so that's why I put this inside. I mean, this doesn't matter. This is a function of x. This is the integration over y. I can put it inside. So that's the same as 1 over root 2 pi epsilon integral dy gy minus gx times e to the minus x minus y square over 2 epsilon. Okay. So this is what it is. And what we want to prove is that this in the limit epsilon goes to 0 is goes to 0, right? That's what we want to prove. Okay. So what is the so how can we do this? There is one thing, I don't know if you know this fact, but I can try to. Okay, I mean, suppose I'm given some function, let's say f of x, f, then you have x here, okay. And so this will be, I can plot. I mean, it will be some curve. I mean, let me take it to be continuous function for the time being, because anyway for us this will be continuous function. So okay. So take this something here, and let's suppose I take 2 points, one point here x and other point y. I mean, the value of this coordinate equal to x or the value of this coordinate equal to y. Now, if you take the difference between these two, so f at y minus f at x, okay, well, that will be simply this. I mean, okay, let me draw it somewhat better. It could be anything, it could be whatever shape you can choose. So this is my f of x, that is my f of y. Okay, so that is this quantity, right? This is the f of y minus f of x. Okay, whereas y minus x this much. Okay, so if I take the ratio now, f of y minus f of x divided by y minus x, that is simply the tangent of this angle. Okay, so but I mean, so but if you now look at this tangent of this angle, this is going to be less than the maximum slope between these 2 points. I mean, if you take this curve and look at the maximum slope, slope is the tangent you draw, right? So if you take so this let's call it theta. This tan of theta, take the absolute value of tan of theta, that's going to be less than or equal to maximum slope of the curve between x and y. Okay. This is well, I mean, in this picture it's very clear. The maximum slope seems to be somewhere here, right? From this picture, certainly that angle is more than this. But I mean, that has to be true. Okay, one possibility is this function f is just a straight line. Okay, that could happen. In that case, the tangent of theta is equal to the maximum slope because the slope is constant, right? And this also gives you that. That's where the equality is. But if you take any other curve which deviates from this, so take this. This is a straight line. Okay. Now the function could be in any possible way. One thing I drew was something like that, right? Okay. Another you could imagine going like that, or maybe even more going around like this. But in every case, you see, if, for example, in this case, the function is going down, and then it has to come up again and meet at the same place, at some place its slope must be more than the slope here, right? Similarly, if some function is going up there and comes back to the same point, at some place it must have more slope than this straight line here, right? So that's a statement. So this is a general statement. The tan of theta is less than or equal to maximum slope of the curve between x and y. Okay. So, but tan of theta is just that. I mean, theta was that. So, it's a f of y minus f of x divided by y minus x modulus. That is less than or equal to the maximum slope. Slope is derivative, right? So, what we are saying is that this is less than or equal to the max of df by dx, okay, where this is the maximum of the derivative between the point x and y, between x and y, right? I mean, I don't know, maybe I can just call it f prime. F prime is a derivative, because this x looks like there's this x, no, but it's not, it's the generic way. So, I can, so let's take the modulus of this guy. This is what we wanted to look at. This is g tilde x minus g of x, right? This is equal to that. So, let's take the modulus of this. That's going to be less than or equal to the modulus of this integral, right? But this guy is, so this guy is less than or equal to 1 over root 2 pi epsilon dy. And now I use this, just instead of f, you replace it by g, okay? So, then you find that this is nothing else but like this is less than or equal to the modulus of y minus x times maximum of, no, let me write it in the next line. So, this is less than or equal to 1 over root 2 pi epsilon dy y minus x e to the minus x minus y square over 2 epsilon times max of dg by dx, maximum of dg by dx. Okay, it says maximum of dg by dx between x and y, but I can as well say maximum of dg by dx in the entire interval from minus infinity to plus infinity, right? Because what the maximum between this x and y is going to be certainly less than or equal to the maximum everywhere, right? But this is a good function, so dg by dx is a good function. So, maximum is some finite number, right? Some finite quantity, okay? So, this I can take it out of the integral because it's just the absolute max of this thing of this dg by dx, but it's a finite number. So, now all that is reduced is just this integral because this is some constant. And that integral you can immediately see it, I mean, you can see how it goes like, I mean, you can actually explicitly do this integral, but I don't need to do this exactly, the integral exactly. I mean, the way to do this integral is to split this integral from, I mean, first of all, shift, rename y minus x equal to y tilde, because everything depends on y minus x, right? So, this integral is same as y tilde. Okay, I can then call y tilde equal to y. So, it's just this integral. Okay. And now you can split this integral, this just becomes 2 times 0 to infinity of y e to the minus y square, because this absolute value of y, right? So, this becomes 2, 0 to infinity, and now I can forget about the absolute value, because for positive y, absolute value is y. So, this integral, but this integral you can immediately do, because you can call y square as some z, then this becomes e to the minus z over 2 epsilon, and this becomes dz dz by 2, right? So, this 2 cancels, and then that integral is just you can perform immediately. It gives you 2 epsilon minus 2 epsilon times 1 basically. So, the whole thing in fact gives you 2 epsilon divided by root 2 pi epsilon, that is the result of all this part, times the max, this which is a number. Okay. Now, you see in the limit epsilon goes to 0, there is a root epsilon down, but up is epsilon. So, finally, what is left over is square root of epsilon up. So, as epsilon goes to 0, this vanishes. Okay. I mean, there is a misprint, I think, in this in the notes. Yeah, there is a, they have forgotten a root epsilon down, okay, in page 233. This is in 233. There is a misprint. They have in the book, it has, they have forgotten to put this root epsilon down. But anyway, so they are finding epsilon, which goes to 0 even faster. But Actually, it's root epsilon, but even root epsilon goes to 0 as epsilon goes to 0. So that proves that that's indeed really true, that for the good function, the Fourier transform is also a good function, and the inverse transform gives you back the original function. Okay. It's not in the sense of almost everywhere. It actually gives you the function at every point, right? Oh, now unfortunately, I still have a few things to. Okay, maybe I should stop.